Ladies and gentlemen, welcome to the third episode of my presentation on Mathematicians' greatest mistakes. In the first episode, I showed just how easy it was to understand the physics of Einstein's gravity equations and solve them, and they were only approximations anyway. So I also showed how easy it was to derive the exact solution to gravity. In the second episode, I removed the 1 in 10 to the 60 odds of the universe existing. The universe is infinite and steady state with a 100% chance of always existing. Observations that were thought to be exclusive to the expanding universe were shown to have simple physical explanations. They were supported by mathematics and observations. There are still the issues of the 73% dark energy and 23% dark matter that mathematicians require to match astronomers' observations and measurements. Dark energy is required to cause the universe's expansion to accelerate. Dark matter is required to match the observed rotation speeds of galaxies. But if the universe is not expanding, why should we be concerned about its accelerated expansion? Well, the results were obtained, so we need to evaluate them and find out what their measurements mean. Figure A is the reason mathematicians think they need dark energy. It is a plot of the measured magnitudes of type 1a supernovae, hereinafter referred to as SNE 1a, and different redshifts. SNE 1a are a particular type of exploding star. They are not easily confused with other celestial events. The magnitude of an astronomical light source is a measure of the intensity of its light between wavelengths of 300 nanometers and 900 nanometers. It is not the total intensity of all detected light. Magnitude is an inverse logarithm relationship. The dimmer is the measured intensity, the higher is its magnitude. A star with a brightness 1% of that of another star has a magnitude 5 times higher than the brighter star. Determining magnitude under the expanding universe theory worked on the principle that light from distant objects would be redshifted both by the distance to the observer and the speed at which they were moving away. Curve D is the calculated intensity expected from SNE 1a at the distance determined from the Doppler redshift equation. It does not include the intensity lost due to its motion of moving. Curve E is the intensity expected from SNE 1a receding from us as observers. It includes curve D. Both present the intensity of all the light. Line A is what the mathematicians were expecting to see if the universe was expanding at a constant rate after the Big Bang. It is sufficiently close to curve E not to make a significant difference to the outcome. Figure B is a typical SNE 1a spectrum at emission. The vertical axis is relative irradiance, a scientific term for intensity. The horizontal axis is wavelength. It's measured in nanometers. SNE 1a emit very little radiation at wavelengths below about 330 nanometers. The curved line is the intensity if the photons were emitted in equal numbers at all wavelengths. Figure C shows what happens when a spectrum is redshifted through different amounts. The overall intensity is reduced, and the amount of the spectrum under 900 nanometers diminishes. At zero redshift, all the spectrum in B is detected and is included in its magnitude measurement. At redshift 1, the blue curve, its intensity has halved and only a small amount of the spectrum is measured in that magnitude range below 900 nanometers. Beyond redshift 1.5, there is almost nothing left to measure. Its magnitude goes very high very quickly. The actual measurement process reduces the magnitude below the calculated intensity. Curve F is what is calculated when the light from the Doppler redshifted SNE1A has been measured for magnitude. Personally, I believe curve F is within the error range of the measured magnitude at different redshifts. Under the expanding universe model, it indicates the universe was either expanding at a constant rate or perhaps slowing down a little bit. But there is nothing in it to indicate the universe's expansion has accelerated. The earlier episode showed the universe was not expanding. We now need to check what those measurements mean in an infinite steady-state universe. Figure A is a quick reminder of the different distances attributed to the Doppler and viscosity redshift measurements. Figure B shows the difference between the two curves up to redshift z equals 1. Now, the D and V curves start to separate at redshift approximately 0.4. On graph C, the vertical axis is the expected SNE1A magnitudes at different redshifts, shown on the horizontal axis. Curve V is the intensity expected from SNE1A spectra being redshift by the viscosity effect for their distance. It is determined from the V curve in figure B. This inset is a reminder that the magnitude differs from intensity because their spectra move through the measurable range from 300 to 900 nanometers. Add that magnitude correction to curve V and you get curve J. Between you and me, I think J is a reasonably good fit with the observed SNE1A magnitudes at different redshifts. Curve J applies for a universe that has a 100% chance of existing forever. Curve F applies for a universe that has a 1 in 10 to the 60 chances of existing now. Your choice. The astronomers who measured those magnitudes at different redshifts did a good job. What they measured was the SNE1A magnitudes expected from an infinite steady-state universe. It was the mathematicians who interpreted it as requiring dark energy equivalent to 17 times the observed mass energy of the universe to give the universe a 1 in 10 to the 60 chance of existing. Is it possible that the whole suggestion about dark energy was due to mathematicians not adding the magnitude correction factor when they calculated the expected magnitudes at different supernovae? Perhaps all they calculated was the expected intensity. That is left for them to explain. Curve J and its calculations show there is no dark energy. The universe is not even expanding, let alone expanding at an accelerating rate. That gets rid of dark energy. It still leaves dark matter. It was predicted from galaxy rotation. The pinwheel galaxy shown is typical of spiral arm galaxies. Galaxies rotate for the same reasons as planets rotate around the Sun. The material from which they were formed did not move radially into the center. Their rotation minimizes gravity collapsing them into their center. Astronomers measured the speed at which different parts of the galaxy rotated. The results are shown plotted in figure A. Theoreticians did not have a good theory for galaxy rotation. They used a variation of Kepler's law of planetary rotation. It predicts rotation should be somewhat as shown in figure B, a rapid increase in speed away from the center to a maximum. That is followed by a decline from maximum speed at greater distances. The astronomers' measurements showed the initial rapid speed increase. At greater distance, the speed did not decrease very much, if at all. The only thing mathematicians could think of was that there was some other form of mass that affected galaxy rotation, but did not have any other effect. They called it dark matter and sent astronomers and particle physicists on wild goose chases for over 50 years to search for it. Planetary motion differs from galaxy motion in important ways. Planetary motion is about a large central mass, the Sun. It contains about 98% of the solar system's mass. Galaxy motion has mass distributed throughout it. To some extent, that can be overcome by using Newton's shell theorem. It states that the gravity of a body of uniform density acts as if all the mass was concentrated at its center, O. Well, a big problem with that is that mass is not uniformly distributed throughout a galaxy. The mathematicians were using a theory to predict dark matter that was not correct. The correct theory is to use Newtonian gravity effects for every star in a galaxy on every other star. Newtonian gravity is used because relativistic effects are too small to make a difference. A team of Sipols and the Pavloviches has done that as an approximation. They divided galaxies into segments as shown in this image of the pinwheel galaxy. The intensity of each segment was deemed to be proportional to the mass of that segment. They used a computer to calculate the effect of gravity generated by every segment on the mass of every other segment. The results are shown on the right. In these plots, the vertical scale is speed in kilometers per second. The horizontal scale is distance from the rotation center in kiloparsecs. A kiloparsec is 3.26 light years. The blue circles represent measured points. The red line is the calculated fit. The green dashed line shows the relative mass compared to the maximum mass for that galaxy. But the overall agreement in this selection is good. They did this for a couple of hundred galaxies. Their fit has been similar to those for about 2/3 of them. No two galaxies are the same. A one theory fits all is not a reality. I suggest those results are a reasonable indication that galaxy rotations are somewhat as expected from gravity considerations of the mass distribution within the galaxy. No dark matter is required. There is one other physical effect that can influence galaxy properties, including their rotation. About 85 plus or minus 10% of the stars in a galaxy are outside the galactic core. Galaxies have a magnetic field that is strongest in the galactic plane and along their spiral arms. Most supernovae occur outside the galactic core. Cosmic rays from supernovae travel along the magnetic fields. Being more massive than electrons, cosmic ray protons make their way into a galaxy's core faster than cosmic ray electrons. This results in a positive charge accumulation in the galactic core. There they are captured by the stars and the small gas and dust molecules. Stars, like our Sun, emit excess protons. They either remain as protons or are captured by gas and dust molecules. This graph shows the cosmic ray flux is highest at about 1 GeV. A significant flux still exists at 10 GeV. Those cosmic rays will keep entering the central core until its voltage gets so high it stops high-energy particles from entering. As this cosmic ray energy curve shows, that could be up to around 10 GeV. The other limiting factor is the arrival of electrons that neutralize their charge. Voltages are relative. The whole galactic central core at 1 GeV or above provides two results. The stars and planets will all be surrounded by a field of the same voltage. They will experience a repulsion from other positively charged particles. They will not have an internal voltage that would blow individual stars apart. This effect has been demonstrated as shown in this Fermi Decades of Gamma Ray Discovery image. Red indicates about 1 GeV gamma rays. The brighter the color, the greater the energy and intensity of gamma rays. The brightest region is in the galactic core, shown in white. That is where the mass density is the highest. The spiral arms have lesser energies and intensities. There are almost no gamma rays outside the galactic plane. There is no solid surface holding the protons in place. They, and positively charged molecules and dust particles, will be repelled. There are two directions in which repelled particles will travel. They can move vertically away from the galactic plane or horizontally along the galactic magnetic field. Not many move diagonally away from the galactic core. Its positive charge and that of the galactic plane pushes them perpendicularly away. Gas and dust particles moving vertically outside the galactic core attract electrons, neutralizing their charge. That gives a stream of dust particles moving away from the center and back to the galactic plane. Protons move faster. They escape further from the galactic plane before they too are neutralized by electrons. That gives these Fermi bubbles. In another effect, protons will also be repelled along the galactic plane. They are held in it by its magnetic field. Incoming electrons will collide with some of them. Their lower energies away from the central core means X-rays are emitted. That is why X-rays are randomly detected with no apparent source. There are other effects this explains that are related to individual stars, but there are two that are related to galaxies. Galaxies have their greatest mass density in their central core. If gravity was the only factor affecting their mass distribution, the stars would collapse to form a small, dense core, as suggested here in A. The reality is shown in B, that galaxies bulge out in their central core. That is a strong indication that gravity is overridden by something. Positive charge repulsion induced by the capture of protons in their central core seems the only feasible alternative. Galaxies have net neutral charge. Any that had a significant net positive electric charge would soon blow apart from their like charge repulsion. A positive charge in the galactic centers means a negative charge in their outer regions. Opposing electric charges gives an inverse square law of attraction, the same as gravity. It is not that electrons accumulate on stars, they don't. They accumulate in the galaxy's magnetic field. The magnetic field drags stars with them. That may seem fanciful to some, but I draw your attention to these two galaxies, Sombrero and UGC 12591. Their most obvious common feature is their stars extend way beyond their galactic plane. Their second feature is their outer reaches rotate at over 500 kilometers per second. That is almost double that of the Milky Way and most other galaxies. There is no physical mechanism by which dark matter could account for both the huge star bulge away from the galactic plane and their high rotational speeds of the outer stars in those galaxies. This description requires a period of high supernova activity to generate the charge effect described. The above indicates one galactic rotation theory does not cover all galaxies. More importantly, it shows that galaxy rotations are approximately as expected. There is neither a need for dark matter nor anywhere for it to fit within the observed universe. Quoting Sipols and Pavlovich, perhaps dark matter is like Confucius' black cat, hard to find in a dark room, especially if there is no cat. In summary, Figure A is the mathematicians' universe. Under favorably selected mathematics, Its odds of existing are 1 in 10 to the 60. The mathematician's solutions included inventing another 10 to the 60 universes in undetected parallel dimensions. A mistake that is out by 10 to the 60 times the mass of the observed universe is about as bad as it can get. Figure B is the astronomer's universe. It is what they observe and measure. The earlier presentation used only 3 space dimensions and time, along with known physical principles and simple mathematics, to show that is all that is needed to explain known astronomers' observations. In the 19th century and earlier, classical mechanics worked well. The mathematics was relatively easy to follow. That changed early in the 20th century. The maths became a lot more complex. However, it need not have been. The apparently complex maths of Einstein's gravity field equations could have been easily solved by alert mathematicians. Here are 2 examples of how easily it was done. One involved a simple rearrangement and integrate terms from Einstein's 1911 paper. It gives the redshift gravitational field strength. The second involved going from this ds² equation to this solution. It was done in a few slides in the first episode. That shows how Einstein, or any reasonable mathematician, could have done it. The strange feature is that many seem not to recognize that any ds² solution was the difference between Einstein's theory and Newton's inverse square law. The full solution to Einstein's gravity is given in this GE term. Both of these solutions used classical concepts to calculate what are called relativistic gravity effects. Had mathematicians recognized that simplicity, they should not have made the 1 in 10 to the 60 part of their greatest mistake. Toward the end of the 20th century, complex maths was considered essential for cutting-edge physics. Complex maths are a problem when the physics they purport to describe is not presented. Very often, there was no physics to support their calculations. They are what led to the mathematician's greatest mistake. Toward the end of the 20th century, complex maths was essential for cutting-edge physics. Had mathematicians recognized the simplicities of Einstein's work, they should not have made the 1 in 10 to the 60 part of their greatest mistake. Mathematics without a physical reason is now an accepted norm in many aspects of modern physics. Fortunately, it is mainly of theoretical interest. As mentioned earlier, the mathematicians responsible for that regarded themselves as the elite, the best of the best. They have definitely set the best record for the biggest mathematical mistake imaginable. This is a reminder of what can happen when mathematics is used incorrectly. With no understanding of the physics involved, they calculated the mathematical odds of the universe existing in its observed state 13.8 billion years after the Big Bang were 1 in 10 to the 60. They considered it was based on the genius of Einstein's work. Even if it didn't seem right, the universe existed, so it must be correct. Other mathematicians offered excuses as to why it could still be correct. One included there must be 10 to the 60 other universes in parallel dimensions that could not be detected. That has no physical foundation. It is not the way mathematics should be used. It seems the mathematicians were too interested in Dirac's mathematical beauty than the sound insight that supported them. The result is the world's best mathematicians claiming the whole universe has 1 in 10 to the 60 chances of existing is reasonable odds. After all, that is what their mathematics tells them, so it must be right. That sums up the lack of reality of mathematical calculations made without a physical basis. An unfortunate result is that some other mathematicians have used the complexity or secrecy of their calculations to insist the results of their work must be correct. Is it too much to ask them to show the physical basis upon which their calculations were made? The former is a one-off. That raises an interesting question. Is the mathematician's biggest mistake deriving the Big Bang Theory with its impossible odds? Or is it the use of mathematics without a physical basis that allowed that huge mistake to be introduced and perpetuated? The former is a one-off. The latter can be repeated many times. It is easily avoided by physics first, mathematics second, and finish off with a common sense evaluation. That even works in the quantum world of individual particles when their structure is known. Much of what was presented in this and the two previous episodes is new to most people. Now, that's true. However, what was presented in the first episode on Einstein's gravity should have been published by 1920 or any time thereafter. That would have made it easier to find the correct interpretations of the other information presented in the second and this slide. That raises the question, why isn't this work published? Most of it has been published as part of my book, The Common Sense Universe. Interested parties can obtain copies of it from any of these addresses. It is not published in the mainstream media because journal policies require complex mathematics and that articles comply with the accepted standard model and general relativity paradigms. This book goes from the smallest subatomic particles to atoms. From atoms to stars, it acknowledges that the work done by previous physicists was the biggest contributor to humanity's doubling of life expectancy, tenfold population increase, and huge improvements in lifestyle comfort in the 300 years from 1700. That was when physicists were doing a great job. And if you don't believe me, just try living without electricity or anything generated using it. That was a physics development. The Common Sense Universe resumes the study of gravity. From there it goes on to the study of galaxies, and it concludes with the large-scale structure of the universe. Some of that has been presented earlier. There is another reason why much of it is not published. In the early 20th century, it was possible to submit papers with complex maths that nobody understood. If they made a testable prediction and showed they matched known unexplained observations, they had a high probability of being published. It applied to Einstein's Foundations of General Relativity paper. Well into the 21st century, you can write a paper that uses known physical principles and easy to understand mathematics to describe every aspect of gravity. It includes how mass alters the property of space that generates gravity, how gravity converts mass to weight, why it affects particles, antiparticles, and photons the same, and anything else you want to know about gravity. A typical journal response could be along the lines, well, it is well written and it offers a good explanation, but it is not standard model paradigm, so we can't publish it. Yet those journals are happy to accept articles that continue the general relativity paradigm that has a difference of 24 times 10 to the 60 between their theory and observation. Such is mathematicians' dominance over physics that they are now hindering further important development. Some suggest they are also hindering advances in other aspects of humanity. Another reason for it not being published is because of other work I have done, the re-evaluation of nuclear physics. It has two noted features. It explains many phenomena that current standard model paradigms can't explain. It also suggests an alternative approach to generating electricity from nuclear fusion. That approach is based on the way fusion occurs in the sun. It matches solar fusion to an accuracy of about 3 parts in 10 to the 7. It does not need tritium, so it does not have any radioactive byproducts. All proposed principles have been independently tested and work. It is the combination that needs to be built and tested. Developing the theory and converting it to an in-principle working design, including drawings and mathematics to support the principle, is not something that can be done in a few months. The principle is scalable from megawatts to gigawatts. Building a trial megawatt reactor gives this technology a far quicker entry and cheaper price than the large-scale projects usually proposed. This study is still a theoretical development project. No guarantees can be given. However, if this fusion project does not work, it places severe restrictions on the future of other fusion work. That concludes my presentation on mathematicians' greatest mistakes. I have shown that there are two major mistakes. The Big Bang Theory is the greatest physical mistake possible. It relied on their psychological mistake of using mathematics without a sound physical basis. I have shown how a sound physical basis reduced the complexities of Einstein's gravity to simple undergraduate physics and mathematics. I have also hinted at physicists' standard model for the structure of subatomic particles. It has serious problems. One of those relates to nuclear physics. I have mentioned an alternative nuclear physics approach that is based on physical principles. It offers a strong possibility of allowing physicists to achieve their ultimate goal of generating electricity from controlled nuclear fusion. Thank you for listening to my presentation.